Let's now look at second order differential equations in more detail. In general, a second order differential equation that is stated in this form could be solved, and solving such a differential equation for P of x and Q of P of x, Q of x, R of x that are some given functions of x would in general involve knowing the analytic property of its solutions. So, to solve this, we should know the analytic properties. What do I mean by analytic properties? By analytic properties, we mean the property of continuity, differentiability, continuity of its function and its derivatives at points where we expect the solution, points where we expect the differential equation to hold, and in addition, wherever the function or its derivatives are not continuous, we would also like to know the nature of singularities of the solution at such points, which in the language of complex analysis that we have already heard of would involve things like finding where the poles and other singularities such as branch cuts of the solutions, if there are, where they are, okay, where they exist. So, to find these, in order to find these in detail, we would need to look at the analytic structure of functions like P of x and Q of x. And this type of analysis is well beyond the scope of these limited set of lectures on differential equations, and hence we would not be able to do justice to this part of the topic. We would in fact restrict ourselves to a very special class of second order differential equations, which are simple enough that the coefficients appearing in our equations, the coefficients of y or its derivatives appearing in the equation are constants. So, this is the special case that we would look at, and usually the differential equations that have P of x and Q of x constants are called differential equations with constant coefficients. So, those are the only type of equations that we would be focusing on in these lectures, in this lecture. And in fact, considering differential equations with constant coefficients, in physics, there is a very useful equation that serves our purpose of solving a second order differential equation with constant coefficients, and that is the one of a driven harmonic oscillator. Well, we are all familiar with the equation of a harmonic oscillator in which there is a force experienced by a particle that is inversely proportional to, so if y is the displacement of a particle, let me choose to write it here. So let's consider a harmonic oscillator whose position is represented by x of t. We know that a harmonic oscillator should experience a force given by the mass of the Hamilton harmonic oscillator times its acceleration, that is proportional to the displacement of the harmonic oscillator, and the nature of that force is, or the direction in which that force acts is opposite to that of the displacement x, and to this harmonic term we could consider adding a term which is proportional to its velocity, which is also such that at any instant that force that is proportional to the velocity is acting in a direction opposite to that of the velocity, and this term arises in a physical situation due to damping of the of the particle, which occurs if the particle moves in an environment in which it experiences a friction or a viscosity, and so on. So this is the equation of, we can say, a damped harmonic oscillator at this stage. Now it is clear that if I have a particle moving in such a situation where it experiences a certain damping, one would expect the particle to come to a halt at some point, and in order to avoid that and let the motion continue, one would need to give certain driving force to the particle, which is the next kind of force that we could add to that, which I would indicate with f of t. The nature of the driving force is that it is completely within our control, so that we could know what type of force we are applying to that particle at any instant of time. So in this sense, f of t is a given function. So rewriting this equation in a form in which we have been used to writing differential equation, we would see that this looks like m into d square x by dt square plus gamma times dx by dt. This constant gamma in this business is usually called the coefficient of friction, plus k of x, where the constant k is often called the force constant, equal to f of t, the given driving force. Now, if we look at this equation, it is obvious that we could read off p of x and q of x as well as r of x, which in this case are should be considered as functions of t, and hence p of t in this case could be identified as by dividing the equation throughout with m, so as to make the coefficient of the second derivative of x identity. P of t is gamma over m and q of t is k over m. It must also be noted that the right hand side also becomes f of t over m in the process. So the differential equation now can be written as d square x by dt square plus gamma over m. Maybe I can do this here. Let us try and solve equations of this form, an equation of this form, and look at the solutions. Since the equation that we have at hand is a non-homogeneous equation, we would expect a solution to this equation to take the form of sum of a homogeneous part x home of t plus a particular solution which I indicate as xp of t, where the part x home of t is a solution to the reduced equation that we obtained from this. And what is the reduced equation? It is the one that we obtain by setting all terms that does not involve x, the independent variable, or its derivatives, to 0. The only term in this equation is f of t over m. So I set that to 0, and the reduced equation that we get is d square x home by dt square plus gamma over m dx over dt plus k over m into x equal to 0. And certainly x homogeneous is a solution to this equation. So if we put x homogeneous into this reduced equation, we would observe that that solves the equation. So the task we have at hand is to find x homogeneous as well as xp, the particular solution. Trying to solve x homogeneous as a function of t first, we observe that the equation we have at hand is d square x home by dt square plus gamma over m dx home over dt plus k over m x home equal to 0. Since this is a differential equation of second order, now we know that we should expect a solution of the form C1 into x home. Let me call it x1 t plus C2 into x2. The task at hand is to find out x1t and x2t. This task gets simplified for the case of differential equations of the type given which have constant coefficients, gamma by m as well as k by m are constants, they are not functions of time in this case. For such equations, this task gets simplified, and the simplification comes if we notice the fact that since this equation is one which involves x as well as its derivatives multiplied by various constants, we should look for a function which has the property that when I take a derivative of that function, I get back the same function, but at most with multiplication by a constant. And what type of a function has this property? That if I take its derivative, any derivative, I would end up with the same function, but possibly multiplied by a constant. And that has to be a function of the type e times alpha t, where alpha is some constant. If I have a function of this type, then it's certain that if I take derivative of that, I would end up with alpha, the constant, times the same function, and if I take its second derivative, I would end up with alpha square times the same function, and so on. So this is in fact equality. So it would be good for us to start with a function of this type and check if there is a solution of this type exists for some value of alpha at least. So let us substitute this form of a solution for x home of t in here. Substituting this into our equation, we get the first term on the last term on the left hand side to be k over m into e to the alpha t. The next term to be gamma over m into dx home by dt, we know is alpha times e to the alpha t. Plus the first term to be alpha square times e to the alpha t. And this type of an equation would indeed solve it provided alpha square plus gamma over m alpha plus k over m is equal to 0 for some value of alpha. And what are the possible values of alphas for which this could solve this equation? And that's going to be given by the roots of the polynomial in alpha that we have at the left, on the left hand side of this equation. And that is easily found to be minus of gamma over m plus or minus square root of gamma square over m square minus 4 into coefficient of alpha square, which is 1 into k over m, the whole divided by 2 times the coefficient of alpha square, which is 1. So those are the possible values of alpha for which this will be satisfied. And that gives us a solution of the form x home t, which have the form C1 into, let me term these two possible roots as alpha plus and alpha minus, which take the values minus gamma over m plus square root of gamma square minus 4k over m whole divided by 2, and alpha minus taking the value with the negative relative sign between the terms in the root. So that I could write the solution as C1 into e to the alpha plus t, where alpha plus is the one root with plus sign in between, and e to the alpha minus t as the second solution. And the general solution to the homogeneous part of our differential equation comes out as x home t equal to C1 into e to the alpha plus t plus C2 into alpha e to the alpha minus t. Usually, what kind of features would we expect for a solution of this type? Physically, it could happen that in the particular case at hand, the discriminant given here, the form gamma square over m square minus 4k over m under square root. Well, I don't need to consider the square root. This discriminant gamma square over m square minus 4k over m, which is the part that appears inside the square root, is either positive or negative, or in fact equal to 0. There are three distinct possibilities for the discriminant appearing in the root, which allows for 3 different types of solutions that display 3 distinct types of physical properties. And those 3 distinct solutions can be read off, or the physical properties of the solutions can be read off for each of these cases. For instance, when gamma square over m square minus 4k over m is greater than 0, so let me call this in short discriminant. When the discriminant is greater than 0, it implies a solution that is of the form e to the alpha plus t, where alpha plus is certainly going to be a number that, a real number that is negative, and hence a decaying solution. And the same is true for alpha minus, where the time it takes to decay varies between these two solutions. So these solutions indicate a displacement. These solutions indicate a displacement of the particle which quickly decays down. In terms of physical description, this is often called overdamped oscillator. This is a situation where the oscillator is damped in an extreme way, so that it comes to a halt very quickly after giving an initial push. So this is an overdamped oscillator. The other possible case is when the discriminant is less than 0, is where you have this number being a negative number, its square root giving us an imaginary number, in which case the solution would display oscillations, and the roots e to the alpha plus t and e to the alpha minus t are going to be the roots that appear in the solutions e to the alpha plus t and e to the minus alpha t are going to be complex numbers, and thus these solutions would exhibit the property of sustained oscillations, or oscillations that sustain for a certain time, after which it decays down to 0. Finally, the third case is the one where the discriminant is indeed 0. By the way, this is often called underdamped. Underdamped oscillator. This case is called underdamped oscillator, where the oscillations do not die down quickly, but dies down only over a period, or over a certain duration. And the third case, when you have the discriminant vanishing, is where you have a certain interesting work that need to be done, and it is often called the critically damped case. Where you have a problem emerging, a mathematical problem emerging, that when the discriminant is 0, the roots alpha plus and alpha minus seem to overlap. And thus, the two solutions which we had initially chosen as independent solutions end up now coinciding, one being a multiple of the other. So, in such a situation, the solution, general solution that I have written down here seem to fail. So, we are in need to find a solution which is independent of the solution of the type e to the alpha t. So, this is the task that we have at hand in order to complete this exercise. Okay. So, it is clear, however, that although the two roots have coincided, we have at least one solution at hand, which is e to the alpha plus t. Namely e to the alpha plus t. The task at hand is to find a second solution. Okay, in cases such as these, where one of the solutions, let's say y1 of x for a differential equation is known, there's a method, simple method to find a second solution, which often works, and that is to choose the second solution y2 of x to be one which is obtained by multiplying y1 of x with some unknown function which we choose as v of x. Okay. Since y1 of x is already a solution, we know that for a differential equation d square y over dx square plus p of x into dy over dx plus q of x into y equal to r of x. By substituting y1 of x in here, this equation would be readily satisfied. Well, sorry, this is 0. This equation would be readily satisfied. Now, if we choose y2, or if we expect y2 to be of this form, I should be able to substitute y2 of this form also into the same differential equation and obtain the equation d square of v into y1 by dx square plus p of x into d by dx of v into y1 plus q of x into v into y1 to be equal to 0. And if we evaluate the derivative of v of y1, v into y1, we get it out to be v into derivative of y1 plus dv by dx, derivative of v into y1. And the second derivative goes on to become the derivative of this right hand side, which takes the form v into d square y1 by dx square plus twice dv by dx into dy1 by dx plus d square v by dx square into y1. Substituting these expressions back into the equation, we get the following. V into d square y1 by dx square plus p v into substituting this into the second term, we get v into p into d y1 by dx plus, writing this as v into q, q of p of x, in fact, q of x into y1 as one piece of term. Next, by substituting these terms into the first and obtaining d square v over dx square into y1 plus 2 into dy1 by dx into dv over dx, all coming from the first term, plus y1 into p of x into dv over dx, all of which have to sum up to 0. Okay. Now observe that in the first three terms, v is a common factor which can be taken out and placed outside the bracket in which the remaining terms are collected, and the term inside the bracket is 0 since y1 is known to be a solution of that differential equation already. That's a given, that solution y1 is already known to us, and thus this is 0. Then our equation, that is this equation, reduces to basically, so that is 0. Then this particular equation reduces to just this, which, if we observe, involves only dv by dx and its second derivative, d square v by dx square. That is not difficult to solve, provided we rewrite that equation into the form d square v by dx square divided by dv over dx equal to minus 2 into 2 over y1 into dy1 over dx plus or minus p of x. Observe that since y1 is already known solution, we know its derivative as well, and the right hand side is completely known. P of x was already known as a part of the differential equation. So this allows us to integrate this equation to obtain the left hand side as logarithm d by dx of logarithm of dv over dx. And right hand side also as minus 2 of d by dx of ln of y1 minus p of x. And thus we see that dv by dx could be obtained as, integrating this whole equation, we get minus 2 into ln of y1 minus integral of p of x dx. Well, this is ln of dv by dx, or we get dv by dx dv by dx out to be exponential of this, which is exponential of minus 2 ln of y1 is ln of 1 over y1 square. So we get, exponentiating this, we get 1 over exponential of minus 2 of ln is ln of y1 minus 2. Then exponentiating the remaining part, we get exponential of integral minus p dx. At this stage, we could write this a little more in a little more simplified form. E to the ln of y1 to the minus 2 is nothing but 1 over y1 square, and then dv by dx is of the form 1 over y1 square into e to the minus p dx. At this point, it is easy for us to integrate this equation and obtain v of x as integral dx of e to the minus of integral p dx over y1 square plus a possible constant. So since we are looking for the form of the solution, we are not particularly interested in putting a constant there, since we are only interested in obtaining a second solution which is independent of the first solution, a second solution which is independent of the first solution y1. It is sufficient for us to look at the functional form, x dependent part of v of x. And once we obtain this, we know that the second solution y2 of x is y1 of x multiplying this whole thing, y1 of x multiplying integral of e to the minus p dx over y1 square. Okay, now coming to our case of a critically damped oscillator. We have observed that in our case p of t, we had taken t to be the independent variable, to be the constant gamma over m, and q of t we had noted to be k over m, and finally we had a solution, one solution, which was x1t, which existed to be in the form e to the alpha plus t, where alpha plus was the root of that equation, unique root of that equation, where the discriminant was 0, and it took the form minus gamma over 2m. Remember, the discriminant in this case, gamma square over m square minus 4k over m was 0. Now, having obtained one solution, we could write the second solution x2 of t as x1 of t into integral dt of e to the minus p dt, where p was minus gamma over m, and since gamma over m is a constant, I could bring it out and evaluate the integral as integral of dt. Now, integral of dt is nothing but t. So, we get minus gamma over m into t. the whole divided by y1 square, which in this case is x1 square, which is e to the 2 times alpha plus t. Now, observe that alpha plus in our case is minus gamma over 2m. So, 2 times alpha plus is minus gamma over m. So, this factor e to the minus gamma over mt is identical to the factor that exists in the numerator, and they cancel, and the integral basically reduces to x1t into integral over dt of 1, and thus gives us t times x1t. T times x1t. Since x1t is of the form e to the minus gamma over mt, x2t is now t times e to the minus gamma over mt, and the general solution will be of the form x of t equal to c1 into e to the minus gamma over mt plus c2 into e to the minus t times e to the minus gamma over m. So, this much is the solution to the homogeneous part of the differential equation. And once we have a solution to the homogeneous part of the differential equation, we could now go on to find solution to the driven harmonic oscillator, which would also involve integrating the function on the right hand side, which indicates the driving force f of t, which is usually given, and this had to be done separately, and there are techniques to do this as well, which will help us to solve the entire non-homogeneous differential equation. D square x by dt square plus gamma over m into dx over dt plus k over m into x equal to f of t, and part of the discussion of how to obtain or how to obtain the solution or obtain the particular solution x p of t will be done in the tutorials. So, after having obtained x homogeneous and x particular, we could write as claimed the general solution x of t as x home t plus x p t. So, as is the case with every instances that we had considered, the constants of integration C1 and C2 need to be fixed by making use of initial values of displacement at certain point, initial values as well as initial values of the displacement as well as initial values of the velocity of the particle at a certain time, let's say t0, and plugging those back into the equation, we should obtain a general solution for a driven harmonic oscillator.